Welcome to Bulk Properties of Solids. You should be familiar with the concepts in GCSE Chemistry or GCSE Combined Science of solids, liquids and gases and their properties. In solids, there are strong bonds between the individual particles that make up the material. These strong bonds can be ionic, covalent or even metallic. And because these bonds are very strong, the particles are very close together. This means that the material has a fixed shape and a fixed volume. It is rigid. The bonds hold the particles in their current structure, and that structure does not tend to change. Because the particles are held strongly and close together, you get other properties as well. Solids have high densities because of how tightly packed the particles are. And because there's no space between the particles, solids are not compressible. In general, solids have an organized structure and the particles vibrate in place. In liquids, the bonds between the particles are weaker. This means that although there is a fixed volume, the shape can change. It flows. And we call materials that can do this fluids. The particles are still close together and are held together by these bonds, and therefore they have a high density. And they are still, just like solids, not compressible. This is how we use liquids in hydraulic systems. There is no organized structure. And instead of vibrating in place, these particles vibrate and flow past each other. Gases are very different. You may have been told that there are no bonds between gas particles. This is not quite true, but the bonds are very weak. This means that there is no fixed shape, and just like liquid, a gas can flow. This means that it is a fluid. Both liquids and gases are fluids. If you place a gas inside a container, then it will expand to fill that space and take up all room inside that container, no matter its size. The volume expands to fill the container. Because the particles are far apart, gases have low densities, and they are compressible. They do vibrate, they move around, they collide with each other, they collide with the walls inside the container, they move randomly. And they have a range of different velocities. At A level, we focus on solid mechanics, bulk property of solids. This includes temporary deformation or elasticity, and permanent deformation. Or plasticity. Continuum mechanics itself is the study of homogeneous and isotropic materials. Homogeneous materials have the same properties and structure at every point within the material, and isotropic materials have the same properties and structure in every direction within a material. Subtle but important differences. If you go on to study materials at a higher level, you'll also study fluid mechanics, or the mechanics of liquids and gases. There are two types. There are Newtonian fluids and non-Newtonian fluids. Newtonian fluids are more predictable. The strain is proportional to the stress, and non-Newtonian fluids, that is not the case. Good examples are the way that custard or corn flour works. If you go into the earth sciences aspect, then you may study rheology, and that is behaviour of things like lava, which is a solid that has fluid properties, or maybe blood, which is a liquid with solid components. In the food industry, you've got yogurt, and in the building industry, you have concrete, all materials that are solids with fluid properties. But at A level, we restrain ourselves to solid mechanics, the study of elasticity and plasticity. Density is a description of how concentrated mass is. Mass in physics tends to be measured in kilograms, and volume in meters cubed. So the unit of density would be measured in kilograms per meters cubed. How many kilograms do we have in 1 meter cubed? In other disciplines, they may be dealing with smaller masses and smaller volumes, for example chemistry. In chemistry, they will tend to measure mass in grams and volume in decimeters cubed or centimeters cubed. So their density measurements will be grams per decimeter cubed, or maybe grams per centimeter cubed. And very often, if they're dealing with liquids, they will measure the volume in terms of millilitres. If you take a solid and you heat it, then the particles inside the solid will vibrate with a larger amplitude. This means that they take up more space. The object will expand. If you take the same object and you put it inside a pressure vessel and you put a high pressure upon the outside of it, then you can cause the object to compress. So when we are defining density, we need to know the conditions under which that density was measured. And we use standard, temperature and pressure. Standard temperature is 0 degrees Celsius, or 273.15 Kelvin. And standard pressure is 1 atmosphere, which is 101.325 kilopascals. In engineering, we need to make allowances for solids and fluids to expand safely. In this diagram here, we have a bridge, and the bridge is constructed of two solid pieces with an expansion joint in between. This expansion joint is made out of a material that can compress easily, for example, rubber. So when this large concrete slab expands and the other concrete slab expands, it compresses the material inside the expansion joint rather than coming up against each other and cracking. In a boiler, we have an expansion vessel, allowing the water in the heating system to expand safely without rupturing the pipes. When dealing with calculations of volume, it's very easy to get tangled into knots when it comes to prefixes, especially when you're converting from one type of measurement to another. I'm going to demonstrate here that if we take a box and we do the measurements in meters, or centimetres or millimetres, as long as the dimensions of the box are the same, 1 metre or 100 centimetres, 1 metre or 1000 millimetres, then you should get the same answer, and that will help you to understand how to treat prefixes. If we analyse this box here, we have side lengths of 1 metre by 1 metre by 1 metre, length, width and height. And if we want to calculate the volume, we must multiply these together. 1 metre by 1 metre by 1 metre. Now if we treat this algebraically, then we can mix these around. 1 times 1 times 1 by metres by metres by metres. And that gives us 1 metre cubed. If we try to do the same for this box, then we should be able to get to the same value. We have our length, width and height. The length is 100 centimetres, multiply by 100 centimetres, multiply by 100 centimetres. Now the centi in each of these cases is a number. It is times 10 to the minus 2. So if I do this same trick over here, then I can find our 100s, our centis, and our meters. Centi is times 10 to the minus 2, and we have 3 of them. We have 3 meters being multiplied together, and then we have the numbers over here. There are 6 zeros. If we simplify, we get 1 times 10 to the power of 6 multiplied by times 10 to the minus 6 meters cubed. These cancel, and you can see that a box that is 100 centimetres on each side is 1 metre cubed. If we do the same for millimetres, then we get the same result. The prefixes need to be treated like numbers. Let's now do a conversion exercise. If I have a block that is 1 centimetre on each side, can I express that in metres? Yes, I can. And there we have it. Each of the centi need to be converted to the number that they represent. They are being cubed together, and then we simplify. Let's now do the same with a 1 millimetre cubed block. there we have it. In physics, when we use the equation for density, it's expected that we're using kilograms and that we're using meters cubed. You can express the units in a different way, but you do need to be careful, especially if you are asked by the question to do a conversion. And as a quick reminder, 1 gram is the same as 1 times 10 to the minus 3 kilograms. Robert Hooke was a British polymath born in 1635. Here is a portrait of him and some of his accomplishments. Here we have the wheel barometer that he developed. Here is a picture of one of the first microscopes that he developed. This book is the Micrographia, published in 1665. In it, he drew pictures of some of the things that he had seen through his microscope. It was in this book that the term cell, as in biological cell, was first used. Here is an ammonite, demonstrating his work with fossils. He was one of the first people to understand that fossils used to be living organisms. Behind him is a map of London. He contributed to the rebuilding of London after the Great Fire. He's holding a chain and allowing it to droop and form a catenary arch. If you invert this shape, then you have an arch that's commonly used in architecture. In front of him on the table is a lens. He did a lot of work with optics and even inferred the wave theory of light. He was able to explain a lot of phenomena, such as the expansion of objects by heat and the pressure of air due to particles. In front of him is a spring, and inside this pocket watch is a balance spring, allowing it to keep time. This portrait of Hooke was produced in 2009, which is quite unusual. Usually these portraits are produced during the lifetime of the scientists themselves. And Robert Hooke did have portraits during his lifetime, but he predeceased Sir Isaac Newton, with whom he had a fractious relationship. Newton published his work on the inverse square law of gravity, and Hooke claimed that he had stolen the work from him. When Hooke died, Newton destroyed all of the portraits that remained. But he is remembered for Hooke's law, which tells us that force is proportional to the extension of an object. If you apply a force, the object will stretch. This force is measured in newtons. The extension, or change in length, is measured in meters. And if we rearrange the equation, we can see that the constant of proportionality, called the spring constant, is going to be measured in newtons per meter. The spring constant is a measure of the stiffness of the material, namely, a spring with a small spring constant will extend a long way when a force is applied, and a spring with a large spring constant will only extend a short way when the same force is applied. The larger the spring constant, the stiffer the spring. Springs are used in many places. You are probably familiar with spring scales, used to measure forces, and also called Newton meters. You may be less familiar with helical springs, or coiled springs. Here is a galvanometer. Used to measure electrical current. The larger the current that flows, the more force is applied to the spring, which turns the needle against the dial and allows a reading of electric current. Here we have another coiled spring attached to a balance wheel. The spring twists and untwists as the balance wheel rotates backwards and forwards under simple harmonic motion. The spring exerts a restoring force, keeping that simple harmonic motion going. You'll find these inside pocket watches, allowing them to keep time. Springs that are oscillating are converting kinetic to gravitational potential energy and back again, such as in this example here. If we apply a force to a spring, we can measure its change in length, its extension, and we can plot the force against the extension. Hooke's law tells us that force is proportional to extension, and that the constant of proportionality is the spring constant. Our graph is directly proportional. It is a straight line graph that goes through the origin, and the gradient is the spring constant. If we calculate the area beneath this line, then we're multiplying the axes by each other, and any force multiplied by a distance gives us work done. The work done on the spring. This would be half the base times by the height, or this, which gives us the amount of energy stored in the spring. We would usually call this elastic potential energy. We can also call it elastic strain energy. These are the same. If we substitute in Hooke's law, then we can also get this equation. We usually call the change in length extension. And that's where the equation for elastic potential energy comes from. If we were to continue our experiment and apply too much force to this spring, then we can damage it, and we won't get a straight line anymore. The line will begin to curve. This is our loading line. If we then remove the force and measure the extension, then we will get a line like this. This is the unloading line. And you'll notice that even when the force has been reduced back to zero, we still have a change in length. This is a permanent deformation. We can also experiment on different materials, like rubber or elastic. We apply a force and measure the extension. Materials like rubber tend to load like this and unload like this. Notice that there is no permanent deformation, and yet the curves are different shapes. If we analyse the area beneath the loading curve, we notice that that area is larger than the area beneath the unloading curve. The area between the two curves represents the energy that has become heat. in the material itself. If you measure the temperature before and after, the temperature will have increased. This is known as a hysteresis loop. We could test materials until they fail, in which case you will get a curve that looks something like this. This represents the breaking point. Typically there will be a straight line section early on that represents elastic behaviour, and then you will get a curved section following it, and that is plastic behaviour. Different objects show different force extension curves, and the shape of the curve depends on the size and shape and material of the object. It doesn't quite seem logical that if you have the exact same material, then they would have different spring constants, just because of their size and their shape. So what scientists have done is they've taken Hooke's law, which tells us that the spring constant is the force applied divided by the extension measured, and they've improved each of these variables to get a constant that is unique to each material itself, rather than the material, the size and the shape. And they've done that by incorporating the size and the shape of the material into these constants. So the improvements made are that instead of force, we now have force applied per cross-sectional area. This means that a wide material is now comparable to a narrow material. And instead of extension, we now have extension as a fraction of the original length, which means that a short material can now be compared to a longer material. And the only variable left is what the object is made from. So we now have force per unit cross-sectional area divided by the extension as a fraction of the original length gives us a new constant that we call Young's modulus. The force per cross-sectional area has been renamed stress, and the change in length compared with original length has been renamed strain. The units, we have newtons and meters squared, so this becomes newtons per meter squared, and we have length measured in meters divided by another length measured in meters has no units, and the units of Young's modulus are newtons per meter squared, or more typically pascals. You may sometimes see the Young's modulus equation written like this. Or even with x as extension. This is an improvement on the Hooke's law equation because it takes into account the physical properties of the material before we then apply our force and measure. The value of Young's modulus is unique to each material, and if you have an unknown material, you can test it, calculate its Young's modulus, look that up in a table, and find out what material that is. If you want to analyse a material, Then you can put it under tension and observe how it changes shape. If you plot the stress against the strain, you will typically get a graph that looks like this. Before it breaks. In the beginning, you will typically get a straight line section. The end of this is called the limit of proportionality. It is the end of the section where stress is proportional to strain. If you want to calculate Young's modulus, then you would take the gradient of the line during that straight section. A little further on, we have the elastic limit. The end of elastic behaviour. This is the elastic region, marked by the elastic. We then have a transition zone, where the material responds in a complex way that's partly elastic and partly plastic. The start of the plastic region is at the yield point, the point at which the material begins to permanently deform. Usually we get a little dip after then, and then the material appears to gain in strength. This is because of behaviour of the particles inside the material. As the crystalline lattice of the solid develops imperfections, these imperfections become entangled with each other and actually cause the material to strengthen. This is called strain hardening. And it occurs up to the maximum strength or ultimate strength. After that point, the material begins to weaken, and it's because those imperfections become too dense and they start to break down. And that's called strain softening. As the imperfections break down, they do so in an irregular way, and you will end up with a weak point within the material. And you start to get something called necking, where the material begins to weaken more and more at one location. This weak spot continues to get thinner and thinner, and eventually you reach the breaking point. Different materials have differently sized elastic and plastic regions. Brittle materials don't have a plastic region, and they will break after deforming elastically only. Some materials have a very short elastic region and then deform plastically. There are lots of different terms to describe the stress-strain behaviours of different materials. For example, stiffness refers to the spring constant. It is the difficulty in stretching an object. Notice that I say object and not material. Hardness is a property that exists on a scale. So you can have some materials that are harder than others. If B is harder than A, then B can scratch or indent A. If I have another material, then it can scratch A and it can be scratched by B. The terms ductile and malleable both refer to plastic behaviour. Ductile materials can be stretched, pulled, and drawn. They are very plastic when exposed to tension forces. Malleable materials can be hammered, rolled, and compressed. They are very plastic under compressive forces. For example, ductile materials can be drawn into wires, and malleable materials can be hammered into sheets. Hardly at all. Brittle materials experience almost no plastic deformation and fracture at the end of their elastic region. Materials like glass and ceramics. The terms strong and tough also refer to similar properties, the ability to withstand large forces. The difference being that strong materials can withstand large static forces, that is, constant forces that increase in a steady way over time, the types of forces that we are applying when we stretch materials. Whereas tough materials can withstand large dynamic forces, forces that change very quickly over time. Glass is very strong, but is not very tough. Glass easily shatters when a sudden force is applied, whereas materials like leather or Kevlar respond very well to dynamic forces. Here is a meme that went viral several years ago. We have a modern white car colliding with an older green car. The damage was almost exclusively to the front of the white car, whereas the green car was largely unaffected. The white vehicle is modern, and it has design features such as crumple zones. The front and the rear of the vehicle are designed to deform under quite a small amount of force, whereas the green vehicle is a lot older and it does not have any crumple zones at all. Whoever put this meme together does not understand physics. The fact that the green car did not deform is not advantageous to the passenger. Older materials were designed to have a very short plastic phase. Meaning that the materials would snap very easily and pass on any remaining energy in the collision, whereas modern vehicles have a very large plastic phase. This means that they can absorb a lot of energy while deforming and not pass that energy onto the occupants. In this collision, we can see that all the damage is limited to the white vehicle. The newspaper articles described no injuries, so it's likely that the occupant within the green vehicle was saved injury by the white vehicle's ability to absorb all of the energy from that crash.